everybody. My name is Jonas Nonn. I'm a scientific assistant of the Institute of Steel Construction at RWTH Aachen University, and I'm going to present a contribution to a developed approach for determining imperfections of LTB tests with directionally true loading using the extended Southwell-method. To the content of that presentation. First of all, I want to give a short introduction to the existing Southwell method for columns subjected to compression. Afterwards, I will go on showing the derivation of an extended version of the Southwell method for lateral torsional buckling to recalculate imperfection values. Keeping this in mind, I will go on with the implementation of the extended Southwell method. My former colleague Matthias Wischolek has developed a special test rig to perform lateral torsional buckling tests with directionally true loading. With the performed tests, we can then derive imperfection values by using the extended Southwell method. We then finally check these imperfections by using numerical investigations. So first of all, I will give a short introduction to the Southwell method, which is also well known by the Southwell plot, and then we'll continue with the extended version of the Southwell method for lateral torsional buckling. From the differential equation of a column subjected to compression with the sinusoidally assumed imperfection shape, we can obtain the analytical function for the lateral displacements. The equation are also known by the so-called Young's equation. Phi EL represent the elastic deflection and phi 0 the imperfection of the initial imperfection of the column. If we now get the ratio of phi EL divided by n as a function of the lateral displacement, we get the so-called Southwell plot. It is a graphical method to determine experimentally a structure's critical load, respectively its imperfection. In the transfer to the lateral torsional buckling problem, it must be taken into account that the imperfection for torsional rotation phi is added to the lateral displacement phi. However, when solving the differential equation system for beams subjected to lateral torsional buckling, it turns out that the corresponding deformations phi and phi are coupled in the eigenmode. If we calculate a numerical simulation of a lateral torsional buckling test considering eigenmode-defined imperfections and further apply the Southwell plot for the lateral displacements phi as well as for the torsional rotation phi, we can then see that the results approximately are on a straight line. But when evaluating real tests, usually phi is not coupled via phi, via the turning radius. Even if a beam would expectionally provide an eigenmode-affine imperfection shape, then just by turning the profile upside down, the subsequent initial imperfection phi 0 and phi 0 are no more an eigenmode affinity. On the right side, the numerical results of the test with non-eigenmode-affine imperfection can be seen respectively the Southwell plots. The results do not lie on a straight line. That makes it different to directly extract consolidated values for the lateral torsional buckling imperfection. In order to investigate whether the non-eigenmode-affine imperfection pair phi 0 and phi 0 can be evaluated, the differential equation system for constant moment can be used. Using a sinusoidal approach for the lateral displacements and for the rotation, the following is obtained. The deformation phi L and phi L can be brought into dependence using the well-known formulation of M critical and N. However, in the search for the general case with uncoupled phi 0 and phi 0, the use of phi and phi are to be used. Then, after some replacement, the following plane equations can be found. If the equation phi-L divided by my squared is then plotted against phi-L on the x-axis and 1 divided by my on the y-axis, then space curves can be found which lie on a plane that is due in place. A sketch can be seen here on the right side. The values v, L and my are from the experimental data. Of course, we can use the same procedure for the rotation phi. With these relationships, an extended Southwell plot can be found. So far to the theoretical backgrounds, which brings us to the experimental investigations. As mentioned before, my former colleague Matthias Wischalek developed a test stand for lateral torsional buckling investigation. In this slide, some sketches are shown of the test stand, and I would like to give a short word about the load introduction, as well as for the support blocks. The load is applied in vertical direction with 1 mm per minute displacement control. Horizontally, the loading jack follows the lateral displacement of the test specimen by means of electric control. Strain gauges are placed at both sides of the load introduction. If a difference is measured, lateral readjusted is made by the electric control. With this procedure, it was possible to avoid lateral forces of lower than 10 newtons. The flanges of the test specimen are arranged in a support frame so that they can rotate independently to each other about the z-axis, so that we are able to create almost fork-like bearing conditions. And here in this slide, I would like to present an excerpt of our test matrix, which we have carried out. 4 tests are presented with different lengths. We have taken the cross-sectional dimensions as well as measured geometrical imperfection related to the middle of the test specimen. The yield strengths had been carried out by material investigations. In this slide, we can see the measured results. All results have been measured in the middle of the field. On the top left, you can see the force as a function of the lateral displacement. It could be observed that with increasing slenderness, an increase of the lateral displacement was measured. And below, the force as the function of the rotation is shown. And for the sake of completeness, the force displacement curves for the deflection is shown on the top right. This table summarizes the final results. With the maximum measured loading, we can also calculate the existing maximum bending moment. The higher the related slenderness is, the smaller the measured bending moment is. Now I would like to go on with the application of the extended Southwell method. On the left side, the measured lateral displacement curves are shown in blue, exemplary for one test. Only the part is shown until the maximum load is reached. To avoid the influence of a rotation during the first stage of the measurement, we choose to transfer only the part with the smooth increase of the curves and approximated the range by regression function, which is shown here in red. We can see it turns out that the mathematically treated experimental data lie in fact not only in space curves, also in skewed space planes. And we have done this procedure for all tests. With the calculation of a regression plane, we can easily determine the intersection with the axis and then recalculate the imperfection values as it had been seen at the beginning of the presentation. The final result is shown in the table below. it turns out that no one of the pairs appear to be coupled by the turning radius, respectively appears eigenmode affine. To check if all investigated imperfection pairs calculated by the extended Southwell-method are a match with the reality, we made some numerical investigation. For transferring the imperfection shape into a numerical model, we used volume elements with isotropic material behavior for the modeling. Sufficient reference points are generated along the beam so that initial imperfection V0 and Phi0 obtained from the extended Southwell method can be imposed. The course of V0 and Phi0 along the beam axis is sinusoidally, so the ratio of V0 and Phi0 is not in infinity with the eigenmode. In the first step, we made a static analysis with boundary conditions at each reference points to generate the shape of the imperfection. In the second step, we calculate a load-bearing capacity, the load-bearing capacity considering imperfections and nonlinear material behavior according to geometrical nonlinear analysis. In this slide, a comparison of the load displacement curves is shown. The curves are determined by the experimental data and are calculated by the numerical investigations. The curves according to the numerical investigations are shown in dashed lines. We can see that the curves are, for all tests, are in a good agreement. A comparison of the load-bearing capacity determined by the experimental data with the numerical obtained load-bearing capacities confirmed this impression. Only small deviations are found. With the help of the extended Southwell method, it can be shown that the test results lie on space curve, which in turn lie planar skewed planes. The intersection of these planes with the axis provides non-eigenmode affine imperfection, similar and analogous to the application of the Southwell method on axially loaded members under compression. Using this imperfection, it can be shown by means of numerical simulation that the load displacement curves are precisely met. With the extended Southwell method, geometrical imperfection can be determined, which allow a precise prediction of the load capacity. Thank you for your attention.